Hello everyone, how's everyone doing? Hope you're doing fine. Sunday, I hope everybody's grabbing their beer, ready for a little chat on a very exciting subject today. Today we're going to be doing line, geometric line. Now how more exciting than that can it get? You might wonder and say, don't you have a more interesting subject to talk about? Yeah, I guess it's not a very exciting subject, very energetic subject, but we need to cover it. And we need to cover it because what happens is the mathematicians, mathematical physicists, they use the point and they use the line. They extrapolate those geometric concepts, and they extrapolate them over into general relativity and quantum mechanics. You probably heard about the point particle, right? What are particles? How do you visualize them? Well, you visualize them as a little point, whatever a point is. For that, we got to go back to Euclid or whatever, but that's what they show. They show a point. That's what they draw. That's what they put on the board. That's what they illustrate. And so you need to get a handle on, what a point is, what the definition is, what it is, and where it came from. Where did we get this word point? And likewise with the line, the line underlies general relativity, primarily because the line stands for distance, for length, for geodesic. They talk about a straight line in four-dimensional space. Well, those are the geodesics. They're curved in our world, but over there they're straight lines, I guess. I don't know. Or maybe it's the other way around. They have all these notions. So we need to get a handle on what are they talking about. Are they talking about a line? Are they talking about a geometric figure? Is that what these people are talking about? That's why, you got to rehash what Euclid did and what everybody, all his inheritors, all his disciples did, thousands of years after him. Where do they stand on these famous words, on these concepts, right, that they're going to be using? So, yeah, it's, for most people, it's not a very exciting subject, but it's like we got to cover that base. Someone's got to do it. I got to do the dirty work, I'm sorry. Someone's got to do it. Before I start, I just want to, one more time, I'll try to remind people constantly. I want to remind people that we have the Rational Physics Conference, the 7th Rational Physics Conference in Bora, Sweden. So I just want to remind you every now and then, hopefully every time, so that you buy your plane tickets, make reservations, plan ahead. Don't wait till the last moment if you're really interested in coming in there. You're going to meet some very interesting people, and who like to talk a lot about the rope model and physics, and also about extinction. And yeah, we get to extinction after we had the beers. Usually, that's the way it typically works. And that's going to be on June 8th, 2019. We're still organizing it, but it will be done for sure. We're going to have it. So get your plane tickets ready. Get your Airbnbs, whatever you're gonna. We have here one of the sponsors, and he says Boris. I hope I pronounced that well, Martin. Boris. I hope that's you won't kill me for mispronouncing that. It says Boris literally translates to living ridge. Living Ridge. I see. Okay, so we're going to the Living Ridge to drink beer now. Hopefully, the Swedish beer is as good as we've seen it everywhere else so far. So we'll find out when we get there. Anyways, I want to get on with the line. Why do we mess around with a line? Why do we care about a line? Well, again, because mathematical physics makes good use of the line. They do borrow it heavily. And not only the line, they borrow the point and the line. In fact, I would say they borrow the point more than they borrow the line. But they do borrow these objects or concepts. We'll find out today. But whatever they are, whether a concept or an object, a figure or an itinerary or whatever it is, they do borrow it and they apply it and they convince you of their theories. So this is not a matter to be taken lightly because their theories are founded on these notions of point and line. We covered the point last time, and maybe I should do a review later on with both the line and the point. But today I'd like to concentrate on the line. We've got enough material there for today. Okay, so let's get started. If we want to start with a line, where do you go? Well, who else? We go to Mr. Euclid of Alexandria. And what Euclid did 300 years before Christ, more or less, that's the best they can locate him. We don't have much information on his life or anything like that, but we know he worked at the Library of Alexandria, and that's about it. And then that he created the elements, which was later borrowed by the Arabs, and they developed it even further, or polished it up, or whatever. They studied Euclid as well. And then we inherited all that stuff back from the Arabs, kind of. Euclid gave it to the Greeks, gave it to the Arabs gave it to us, to us Westerners. I consider myself a Westerner because that's where I was born and lived, so they gave it to us. And yeah, 300 years before Christ, Euclid came up with. He didn't really come up with it, by the way. He kind of made he organized the thoughts of the Greeks, whatever they had discovered until then, until 300 years before Christ, whatever they had invented, whatever they had developed as far as geometry, whatever they had, whatever rules, whatever laws, whatever definitions, whatever axioms they had developed or evolved or whatever by then, he kind of put them together in this book, the Elements, and that's what we got. We got his book. Whether there was a book before his, well, we don't know, and there probably wasn't. Maybe he's the guy who finally sat down and said, "I'm going to write all this down and put that in some kind of order so that all these thoughts that are running around by different mathematicians, we can condense them in one book." So this is like the encyclopedia of geometry, you could say, his Elements. Okay, and that's where we get our starting point. So from that starting point, we look at his definitions, and this is what we find. We find that he's got a set of definitions with which he begins his book. And today we're going to look at definition number 2. A line is breadthless length. Big words. Breadthless length. He also says later on, definition 4, a straight line is a line. Okay, so a straight line is a special kind of line. Apparently, under the word line, he includes, curves. And you might also think of this because he says breathless length. If he's talking about curves, a circle, a circumference, the circumference of a circle, you know, if that's included because we're talking about curves being also lines, well, here you have a line that begins and ends. So it's got a beginning and an end. It ends where it begins, essentially. So I'm not sure that would be infinite, right? But here he's referring to breathless length, meaning not that the length extends eternally, but that it's one dimensional. That's what breathless stands for. Okay, he's and again we have to be careful on how these people translate these things. Okay, this was translated as breathless length. What is the problem that I see with that right off the bat? Well, the problem is this word breathless. Okay, breath is sideways motion. That's what the word breath means. Not all languages have it. Like they don't have it in German, and we don't have it in Spanish either. You know, those two languages for sure. I can tell you, they don't have breath. They use the word with essentially to refer to breath. And breath is, and it's very hard to pronounce that. breath. Okay, breath is different than with, and it's different than latitude. These are three different kind of words, and I'm going to go over that later in another presentation on dimensions, right? But just for your information right now, breath is sideways motion. That's different than width, which is just a dimension in a horizontal plane. And that's different than latitude, which is a coordinate for locating things along a horizontal plane. So these are three different concepts. And so whoever translated the breathless part in Euclid's definition, he should have said widthless length. And he should have said, to be more clearly, he should have said heightless and widthless length, because dimensions come in three flavors. They come in length, width, and height. You need all three of them. You know, there is no such thing as length without width or height. There's no such thing as height without width or length. There's no such thing as width without length or height. You need all three of them because that's what a three-dimensional object is, and all existing objects are three-dimensional. And again, I don't want to get ahead of myself in talking about dimensions. All I just want you to be aware where all this stuff comes from, you know, or to keep these things in mind. Breath, it was the wrong word to use. Okay, at the best he could have done, whoever did this translation, would have been widthless length. But essentially he's saying that it's got no thickness, right? No width, no height really. It's heightless. That's what I want to say, not widthless, but heightless length. It doesn't have any thickness to it, and it's just length without the height, right? And really it would have been better to say heightless width. And I hope you don't have a headache by now. Anyways, the wording is important in that sense. Then the other thing about that is that, you know, if it's breathless length, what was he referring to? Is length a physical object? Is length a geometric figure? And the answer is no. Obviously, if Euclid was talking about length, he was talking about something else. I mean, is length the same thing as a line? Are they synonyms? You know, here I have Euclid's breathless length. You can see it there. Mr. Euclid is writing it for the first time, and you can see what he's writing there on the right-hand side. He's writing a line AB. Okay, fine. That line, as I can show you there, it's got width and it's got height. It's got two dimensions at least. So that's what that line that Euclid drew on the board or on his piece of paper or in his book or whatever. That's what he would have to draw if he's going to represent it. And then you can say, yeah, okay, the line is a geometric figure. I'll repeat that, figure. Okay, it's a geometric figure and it's got width and height. So far, no problem. But that's not what Euclid's saying. That's what he drew on the board. That's what a mathematician, a geometer draws on the board. But what is it that they say? They say it's breadthless length. They're saying it's a length. But length is not a stick. And no wonder it's breadthless. In other words, why is it one dimensional? That's what breadthless means. That's what Euclid was referring to, that it's one dimensional. Okay? And so if the length is one dimensional, actually it's non-dimensional. That would be a more accurate description of length. It's a concept, and concepts don't have dimensions. They don't have thickness. They don't have width. They don't have height. They don't have anything, because they're concepts. And if length is a concept, we've got a problem to say first that it's breadthless. That was uncalled for. He should have said a line is length. That's all he needed to say. And if a line is length, okay, then length is not a geometric figure. So now we have a problem, because Euclid is setting the foundations for geometry. And he's telling us in so many words that this is a geometric figure, and he's going to define it as length. That's where the problem is. He's treating a concept as a physical object. And that's why we're going to run into trouble, not only with Euclid, but as you'll see today, we're going to run into trouble with everyone that came afterwards. Because one is a concept, the other one is an object. One is a figure, and the other one is an itinerary, a verb. And that's where the problem is. Euclid qualified as length, but he's not talking about a geometric figure in that case, and he has not laid down the foundations of geometry. The other one is that he insinuates that this thing continues forever. And that's what is going to come down to us through the ages. That a line, is just infinite in both directions. So they put, I put on in his little drawing there, I'm not sure if that's what Euclid intended, but that's what it is today, that the line is infinite in both directions, which means that, if Euclid intended that the line doesn't stop, we don't have a geometric figure either in that case. Because if the line continues to positive infinity or to negative infinity, whatever that is, it just means it's still growing. And if it's a line, and if it's got to be a figure, it's got to have endpoints. And here you'll see it in his definitions. Okay, here you see it. If you look at definition number 14, down at the bottom there, a figure is that which is contained by any boundary. Okay, so if it's contained by a boundary and the line is infinite, then the line, even if it's a rectangle, an elongated rectangle, if it's infinite, then that means it's still growing. It means it doesn't have endpoints. It is not bounded. It does not have a boundary. And so we have to determine, if Euclid is really referring to, if he's referring to an object or to an itinerary, because we can imagine walking, running, jumping. That can be forever. That we're talking about a verb, something that goes on forever. We can all maybe picture that. The movie doesn't end. Okay, endless love. But here we're talking about something else. We're saying that if Euclid's line is endless in both directions, or even in one direction, it starts here but never ends, then he hasn't finished constructing his line. He's still in the business of building it. In fact, his disciples should still be constructing it at one point at a time. They're still continuing, going on and on and on. So we got a problem. We got a problem because it means that we're not talking about geometric figure. We're really referring to an itinerary. And what they're saying is that itinerary is nonstop. We're talking about perpetual motion. That's what we're talking about. And perpetual motion is not a geometric figure, so keep that in mind. Okay, what happens next? Well, hopefully someone did better than Euclid. I mean, that was 2,300 years ago, maybe a little more, a little less. And I mean, we had all this time, 2,000 years. That's 2,300 centuries since Euclid to improve on his work. Surely someone has done a lot better, right? Well, the answer is no. The answer is we still are using Euclid's line to this day. That's what we have in geometry. How do they state it? They say that a line is undefined. They can't define what a line is. So what do you mean? After 2,300 years, you can't define the word line? They said, no, we can't because, see, it's a primitive concept. Oh, okay, primitive concept. What exactly do you mean by that? Well, it means that, you have to start at some point, like the ABCs of geometry in this case, the foundations. And, we can talk about solids, but solids have to be based on a previously defined structure. For example, you can say the plane, and the plane has to be the foundation of the plane has to be founded on something previously defined. In this case would be the line. The line would have to be defined based on a previous geometric object or concept called the point. But if that argument holds, first of all, we got a little problem because it means that we already have a starting point. That's the point. So if you can say, okay, I'm not going to define the point because it's what constitutes everything else. Okay, well, let's concede that. Now you don't have an excuse for line because the line is made of points, and you don't have an excuse for planes because the plane is made out of lines and points, and you don't have an excuse for solids because they're made out of planes, lines, and points. And the answer they'll give you today is that points, lines, and planes, all three of them are undefined. So they don't know what a plane is, they don't know what a line is, they don't know what a point is. And the excuse is that, we need something more primitive. Okay, so you got it, it's the point, right? What's your excuse now? So that's the first argument against it. The other one is that, in physics, in the world of rationality, in science, we don't define, we define concepts, we don't define objects. You don't define figures. You point to them, okay? You got the Martian coming over. You want to teach him your language, you got to start with the nouns, like I said last time. You point, say, table, couch, lamp. You point and name. That's how you designate, or that's how you, come up with a language of nouns, of figures. You don't define a table. You don't say a table has, 4 legs and, a board over it. That's not a table. A table is what you point it to. Then you can describe it. But first you got to point to it and name it. And so that's the starting point. The starting point here is that Euclid is supposed to point and not define. You should make a drawing. What do you mean by point? I mean, that's what I mean by point. Oh, okay, that's a synonym of a dot. Then we all understand. That's what's staring at you in the face. You're saying, okay, a dot. But then he can't say, well, by the way, the dot is 0 dimensional. What do you mean 0 dimension? It's got 2 dimensions, width and height. What do you mean the line is 1 dimensional? It's got width and height. I see two dimensions. No, that's a pictorial representation of the real line. The real line is something else. It's a length. And so now we have a problem. And it turns out it's not even a length, and that's what I'm going to cover next. Here we have Mr. Herman Whale, a guy who I've studied a little bit in some detail. And Mr. Herman, he wrote a book called What's My Line? Now, that's a lie. No, he wrote a book called Space, Time, and Matter. And in Space, Time, and Matter, if you look at this book, he starts out by laying the foundations of geometry. He goes over the foundations of geometry as an introduction to general relativity. The book is about general relativity. And he was a colleague of Einstein. He went to Princeton. So Herman, in fact, he died, I think, in the same year. They both died in 1955, I think it was. So, they knew each other and they probably worked together, etc. And it's important to know that Einstein once said that all his colleagues, I don't know if he singled out Whale, but all his colleagues, they treated him like an old piece of furniture. They all got away from him like from the leprosy, from a leper. They treated him as a crank the last years of his life. And yeah, Whale, he wrote his book in 1929, so that's when Einstein was still, roaring. It's when Einstein later on went to Princeton and was with Whale that he was treated like an old piece of furniture where people, avoided him in the hallways. And Whale was probably one of those, I don't know, because Whale continued to believe in general relativity. Einstein, as far as I'm concerned, did not. No longer believed in general relativity. He essentially, like he told his friend Bezo, he didn't believe in, he stopped believing in the field concept, the concept called field, which is what he was famous for. He never got a Nobel Prize for it. He was famous for inventing the field equations, 1915, 1916. Okay, so what does Mr. Whale say as far as what a line is? Oh, very simple. He says, look, a line is 2 points. Okay? He says the straight line, he starts out with this already on page 12, he goes over Euclidean space, as they call it, Euclidean geometry, which is two-dimensional geometry, essentially. And he says a straight line is determined by two of its points, page 12. And there you have the 2-point line. They call it the line AB. Okay, here you have 2 points. And the question is whether that's a line. If you look at the lower left, you see a red and blue dot there. And then to the right of that, you see a solid one-piece stick, black stick. If you show those two images to a kindergartner and say, could you identify which of these two images is a line? Which one do you think he would choose? Which one would you choose? Yeah, I think we would all choose the one on the right. The one on the left, the 2-point line, I don't know. Doesn't look like a line to me. It looks like two balls. Okay, it looks like ping pong balls. That's what it looks like. King Kong's balls. Okay, so that was his first introduction into the word line, right? He's trying to define what a line is. Next, he continues with the distance, the length line of Euclid. He goes like this. He says, the straight line lies evenly between its points. So let's assume, for the sake of argument, that points is refers to two objects, two figures. We'll just assume that, and we'll consider the points as being dots. Okay. What Whale is saying is that the straight line lies evenly between its points. Okay, if he's referring to length, we got a problem because we got the breadthless length, and besides that we have, in other words, a one-dimensional length. And length is a concept, so it's not even one-dimensional. It's non-dimensional. Concepts don't have dimensions. So you can see on the bottom right, breathless length, the arrow points to nothing. That's what uh, Whale's distance line looks like, or length line looks like. If, on the other hand, we define length as a distance, we're not even talking about length. We're talking about empty space between two dots, which is the image on the lower left. So which is it? Are we talking about, is the straight line the distance between 2 points? Is a straight line a one-dimensional length, or better yet, a non-dimensional length? What are we saying when we say that it lies evenly between its points? And then, of course, if you add to this that the word point means zero-dimensional nothing, there is a point is not a dot, a point is a location. We're talking about the distance or the length between two locations, whatever that could possibly mean. We're talking total abstractions here. And this is supposed to be, you know, the foundations of, these are supposed to be the foundations of geometry. What is geometry? The study or the research or the science of shapes and sizes to begin with. You need a shape and you need something in there. And these people are forgetting about the somethings, and they're working with nothings. They're working with concepts. Okay, that's where they start. Okay, what's the next notion that Mr. Whale comes up with? And again, these are new concepts that came after Euclid. Okay, these were developed after Euclid. Probably did not have any idea of some of these notions that were, you know, popped into geometry later on. And this is the hinge. Okay, here Mr. Whale says not only the straight line but also the plane is based on a property of rotation. And when you look at his book, what Whale is talking about is the fact that if you rotate a line as long as every point remains on the line, then you have what is called a congruent transformation. Okay, so the line doesn't get twisted or bent or warped or whatever. Okay, but he talks about rotation. Now we're talking about the motion of planes and lines. He's treating it like, you know, a hinge or, that goes around a stick. Okay, think of a hinge that goes completely around, right? A stick run through the center, and the rotation of the hinge determines the straightness of the line and the definition of the line that serves as a stick inside, you know, the hinge. So that's another notion. Okay, let's look at another notion here. This is my favorite one because this is this is the one that's probably used, well, one of the ones that's used the most, and that's the row of apples. Now we have, you know, the row of apples line. And here Whale says a congruent transformation which transforms A into itself and all points to the right of A into points to the right of A and all points to the left of A into points to the left of A leaves every point on the straight line undisturbed. So he's saying the straight line is made of points, and he confirms that later on, 4 pages later. He says, we shall obtain an array of points on the straight line under construction. Okay, we got a couple problems here because Whale is not finished with his line. He's constructing his line. And if his line is infinite, as he will say later on, you know, we're talking about apples that just go on forever. You know, all these points just go on forever, and because they construct lines. See, in science, we don't construct dogs or trees or rocks. We point to them, and it better be a finished product when you point. What these people are saying, you can't point to a circle. You got to construct it point by point, and you can't point to a cube. You got to construct it point by point, or plane by plane, or line by line. They construct geometric figures. Well, give me a call when you finish sculpture. Yeah, when you finish your grand, sculpture, give me a call so I can see your finished product. Right now, you're still working on it. Especially if you tell me that the line is infinite. You haven't finished your line. And then you can't even call it a geometric figure because, like Mr. Euclid says, if this thing continues forever, then, what are we talking about? Are we talking about length? Are we talking about an itinerary? Are we talking about locations that go on forever? Because we're not talking about really a line. We're talking about a kangaroo that's jumping from point to point and he's still running. He's still jumping, which means that, from a geometric point of view, what all these people are saying when they say, especially when they say that their line is infinite, they're talking about motion. They're not talking about a perimeter or a surface of a geometric figure that you can point your finger at. That's what I'm saying. What these people are referring to is something else. They're referring to all these points which represent locations. And what is location? We're talking about not locations of different apples. In this case, we had that, but we got another one, which is, let me show that first, maybe. Here we have the itinerary line. This is the other version of the many apples. But here we have one apple, and we're talking about the translation of an apple. In other words, Whale says, let A be a translation which transfers the point A to A sub 0 to A. So he's talking about, he's talking about moving one apple, not about a row of the apples. And he says the straight line is derived from a point by an infinite repetition of the same infinitesimal translation and its inverse. Okay? So what Whale is saying here is that, not only is the apple at different locations, we're only talking about one apple here, okay? And the apple is at different locations. It's rolling, it's moving, it's sliding, it's whatever it's doing. And it goes on forever because he's talking about an infinite repetition. And the other one that you should keep in mind is the word infinitesimal. I hate to spend all day on that word, but it kind of, I'm just going to give you a forewarning on that. Infinitesimal means small. That's what infinitesimal means. And so how small is small? I mean, what is this infinitesimal translation? How far am I supposed to move that apple? Am I supposed to move it an inch, or is that too much? Maybe I'll move it just a centimeter. How about a micrometer, or how about an angstrom? I need to know how far I'm going to move that. He says infinitesimal. But by infinitesimal, he really means zero, which is what all mathematicians want to convey with the word infinitesimal. When they say infinitesimal, it's a buzzword that should immediately shock you, because you should keep an ear for it. Infinitesimal in mathematics means zero. That's what they want to mean. See, you have the limit as x approaches 0. Well, approaches doesn't mean 0. Infinitesimal means approaches. It doesn't mean 0, that you're standing at 0. And these people use, dualities. They love dualities. They say infinitesimal means approaches 0, x approaches 0, but, it's also 0. So whenever they use the word infinitesimal, most of the time when they're talking qualitative stuff, they mean 0. They mean nothing. And so infinitesimal translation. But anyways, infinitesimal translation means it moved. And if it moved, you're talking about one apple covering different locations. Okay, and that's different than having, a row of apples. That's a different concept altogether. And of course, he's got another one similar to that one. And you can think of this as sliding. So you can jump, or you can slide, or you can just transfer the apple. There are many ways of looking at this. This is the sliding version. You slide the apple through the rabbit's hole, okay, and it creates a trough in there, okay. So he says there is one and only one translation which transfers the arbitrary point A on G to the arbitrary point A star on the same straight line. Okay, so he's got this other notion, this sliding or this trough, this channel type notion of line. Does he stop there? No, he's got a couple more. Here he's got the stick, which I love too. Here's the stick. Let's see if I can get it in there. Okay, here's the stick. This whale stick. All the points which we obtain. He's taking the row of apples, okay? Keep that one in mind. All the points which we obtain finally fuse together into a linear continuum. You like the word continuum because continuum is a concept which they turn into a noun. They turn this adjective, continuous, into a noun. And what they mean is that continuum is some kind of stick that is made of a single piece. That's what they call continuum. And they'll use this fancy word and they say, in which they become embedded, giving up their individual existences. We no longer have dots. Now we have the continuous single piece stick. Okay? This description is founded on our intuition of continuity. Okay? So you see what Whale has done here with a line. He took all these apples and then he fused them together. They lose their individuality, their individual existence, and they become a stick of apples, all blended into, meshed into a single stick. But again, if we're talking about a single stick, are we talking about a two-dimensional stick, or are we talking about motion and or itinerary or a series of locations? And yes, motion in that sense, you could say is continuous, but it really is not. When you come to think of it, motion is discrete because it means the object is at a second location, is a different location. So try to make an image of that. Here you have the movie, the universal movie. If an object can only have one location, once it is at a second location, I don't care how infinitesimal that other location is, how far away you put it from its original location, if it has a different location, that location should fall in a different frame of the movie. This is a conceptual issue. This is not an issue of, oh, let's define this or that. No, it's a conceptual issue. If motion is two or more locations, and we're talking about motions, two or more locations means two frames of the universal film. And so you're talking about two now. Motion is always two, at least, as a minimum. And so if the dot or the location is at two locations, right, then you need two frames of the film. In that sense, motion is discrete because location can only be fit in a picture. Motion can only be fit in a movie, in a strip of film. That's a conceptual issue. I hope you understood what I'm trying to say here, okay? Anyways, Whale, he blends all this movie, and he forgets about what's in the frames, and he just takes the whole film strip, and he says, look, I got a line. Yeah, but how about all the frames that you have that make up your film strip? You got all these frames. They're discrete, right? Because each one is chopped off at the little lines there that the frame has. And he gets rid of all that. He just blends it into a single stick. But then he tells you again that you're staring at a 1D line made of zero-dimensional points. You figure it out. Okay, does he stop there? No, we got one more. And it's, you say, what else could a line be, right? Okay, here we have the final line. He's got more really, but I'm going to stop here, okay? Here it is, the number line. Whale finally says, okay, forget about locations, forget about points, forget about apples, forget about one apple rolling or sliding, forget about turning all the apples into a stick. I'm going to turn this whole line, I'm going to take my magic wand and turn it into a bunch of numbers. a series of numbers. And he says if we take all possible whole numbers as values of n, this array will become denser in proportion as n increases. And he goes on to, if you look at his book, you'll figure out that he just goes on dealing with numbers after that. So whatever he presented at the beginning has nothing to do with what he's going to use it for later on, especially as a foundation for general relativity. He's going to be talking about distances. He's going to be talking about lengths, not so much about lengths, but surely about distances, because that's what general relativity deals with. He's going to talk about geodesics, and he's going to talk about numbers. What's any of that got to do with the stick made of a single piece, all these apples that he blended together and turned into a stick? What's one thing got to do with the other? What does distance, length, geodesic, numbers, what do any of those have to do with geometry? I thought geometry was a study of shapes and sizes. I don't know about sizes, but certainly about shapes and relations between shapes, and maybe relationships also between angles, you know, that kind of thing. But what's all that got to do with lengths, distances, geodesics, itineraries, numbers? Looks like, what does any of that have to do with geometry? And that's essentially what they're doing. They're creating a foundations, not for geometry. They're creating a foundations for all this stuff that they're going to use for things like general relativity or string theory. What's a string? What's a string? String is a vibrating line, a 1D line. You can look it up. Don't take my word for it. Look up the 1D strings. What are they talking about? They're talking about, you know, a line. And, you know, that string wiggles. So you would think it goes into a second dimension when it wiggles. And they keep calling it a 1D line. So are they talking qualitative or quantitative? Are they talking about a length, a distance? Or are they talking about Euclid's 1D line? I mean, what are they talking about? And again, they use the geometric figure called line, the word line, which you know what we mean. You know, we mean that stick that you see there that we drew on the board. But you're supposed to think of that as 1D. Okay, I'll even go as far as that. And now they're going to vibrate it into 2 dimensions. They say, see, it's a 1D line. A vibrating 1D line. Well, no, as soon as it moved up, it turned into a 2D line. You know, it bent or whatever. It warped. It's like the qualitative stuff just goes from one ear through the other, nothing in between to stop. Okay, so let me put all these lines together so you can see them in one picture, one nice, beautiful picture there. And here you have the 2-point line. Is that a line, two dots? No, you would think a line is more like a stick, right? Like maybe the one below down there, a whale stick. You would think that's a line. That's what kindergartner would recognize as a line. Then you have the in-between line. Okay, the between 2 points. Are we talking about a distance or are we talking about a length? Either way, we're not talking about a stick. So that green part that I drew in there, that's misleading. That's false. The line that is between the 2 points is not a line. It's a distance. That's what's between 2 points. And if he wants to put something in there, he should draw it. And for sure, that's not going to be one-dimensional or even, you know, constructed by zero-dimensional points. Whale's hinge, you know, you got the translation, the rotation, the row of apples. You know, that's a neat line. They just put a bunch of points one next to each other. We don't know how close they are. We don't know if they're touching one with the other, how small the points are, because, I mean, it'd be nice to know how big the points are to find out, you know, how much space is between their bottoms, or between, like in this case, between the leaf of the apple. Okay. And also remember something, that each apple, in order to maintain its individuality, it has to be, from a conceptual point of view, it has to be encapsulated within space, you could say, right? In other words, they've got to be completely isolated from the one next to it. What Whale does, at least, he takes that and turns it into a stick. He just blends them. Okay. Then we have the rolling apple. That's just one apple that is at different locations. Maybe it rolls, maybe it slides like in the plowing line below. Maybe it just creates a channel. Maybe it just is sent so that it kind of what is it called? What is it? The Enterprise. What do they do? The word skipped my mind. When the guy just misses all the space in between, so he's reconstructed at another location. The word just escaped me right now. Anyways, so it doesn't go through all the intermediate locations. And then you have the number line. All these locations, all these apples are turned into numbers. So you've got your pick. You've got enough there to keep you busy. What is a line? You go home and your dad asks you, "Okay, son, what did you learn in school today?" "Well, I don't know, not much, Dad." "What did you take?" "I took geometry." And what was the subject matter? What was the line? And what is a line? "Well, that's the point. I have no idea." Because, they have all these notions of line. And most of them, except maybe the stick, the row of apples, except those two maybe, all the others have nothing to do with geometry. They're not geometric figures. And that's the main problem. We're not talking about geometry anymore. And you say, "Well, Bill, you're peddling or fiddling around too much with language. You're doing semantics." But see, they're going to use this later on as the underlying foundations of their theories of general relativity, of string theory, of quantum mechanics. That's why you have to be careful. They end up saying, "Oh, what is a particle? It's a vibrating field." What is a black hole? "Oh, it's a bunch of mass." And what is a mass? Well, it's just a dot, a point with infinite mass. So you got to be careful because they're going to use this, for their theories. It's not a trivial issue. And if they're going to do that, okay, then take the trouble to define it properly. Then there's the other issue is if you're going to say, look, the point is really a location, a line is really an itinerary or a bunch of numbers, whatever you say, then don't call it line, because you confuse people. If your line is a bunch of locations, use the word location. How's that for a revolutionary proposal? Use the word locations. Say, I'm not talking about lines. I'm not talking about a stick. I'm talking about a bunch of locations on a plane or on a solid, on a cube. Then people understand. Say, "Oh, you're talking about locations." But you call it point, or you call it line, and you confuse people completely, because people say, "Okay, what do you mean line? Are you referring to the physical object, to the two-dimensional stick, or are you referring to a bunch of locations? Are you referring to an itinerary, or are you referring to a bunch of apples?" What are you referring to? That's where it gets confusing, because the word line at that point could be anything. And you gotta stay tuned and say, what is he referring to at this moment in time? Is he talking about this or that? That's where the problem is. Okay, so let me get down to the conclusions for today, at least. And here we have a little summary. Geometers still use Euclid's breathless length as the definition of line. Essentially, nothing has changed. They still think of line as a one-dimensional length, distance, or itinerary, or a bunch of locations, however you want to see that. That's what the word line means today, and if that's what it means, it has nothing to do with geometry. And second, if that's what it means, then they should use the word length and not the word line. They should use the word itinerary not the word line. They should use the term like row of apples, a bunch of numbers, the number line, whatever they want to, whatever they really mean. They should not be confusing you by saying line. Okay. Euclid's line fails because it's incessant. It just goes on forever. He's really referring to length or an itinerary, really, because length in Euclidean geometry, keep in mind, is distance. They're synonym, and what they're talking about is measurement. They're saying they're going to extend the measuring tape, and again, we're talking about the itinerary of the front of the tape. That's what length is in there, because they're talking about measurement, they're talking about numbers, they're talking about a concept, a mathematical concept. Okay, they're not talking about the space between two tables or the length of a table, meaning that it extends from here to there qualitatively. No, they're talking about, look, let's pull out the tape and measure it. Oh, it measures 1 meter. That 1 meter is that length. And the separation between two tables is 1.5 meters. Well, that 1.5 meters is the distance. That's why they have defined distance and length to be synonyms, because to them it's 1 meter either way. Okay, it's according to Euclid, it's one-dimensional. That's not a figure, because all figures at least are two-dimensional. So if it's not a figure, does it even belong in geometry? I would say no. If he's referring to an itinerary, he should use, again, the word itinerary or a bunch of locations or anything you want, but not the word line. And then again, location, itinerary, numbers are not geometric figures. So he cannot treat them as such. We're talking about concepts there and not about objects. Geometers, especially Whale, in this day and age, he died already, but I mean, his disciples essentially say the same thing. They confess that they don't have a definition for line. No kidding. We don't define figures. If they're trying to define the word line, then they're defining a concept. We don't define objects. We point to them and name them. You point to a table and say table. That's how you so-called define a table. You point to it, and then the ET understands what your word table means. And that's the way you should do with line if line is a geometric figure. If line is something else, then yeah, you want to define it. And then, yeah, of course, they're going to have trouble defining the word line because they want to have their duality in there. They want you to think that it's a geometric figure, the two-dimensional stick. And at the same time, they want you to think of it as an itinerary. And that's where they run into trouble. That's why they can't define it. And again, we have all these notions that you saw in Mr. Whale, 2-point, the distance, the length, the locations, itineraries, numbers. None of those are lines. A line is a stick. That's what it is. That's what you see there. That's what we objectively have before us. That black line that you see there, that's the line. And as you can see, it's got height and width. It's got 2 dimensions. If the geometers can't use that for anything, then they should not call it a line, because that's what a line is. And that's the border of a square, and that's the border of a cube. Those are the lines. If they don't like that, if they can't use that, well, then maybe they're talking about something else. Maybe they're talking about itineraries. Maybe they're talking about locations. And that's what they should call them. That's my point. And then the last one is, yeah, if geometry underlies mathematics, and that's going to be used or extrapolated to physics, well, then mathematics is not the language of physics, period. I mean, these people can't kid themselves and say, oh, we're doing physics here. And they use words such as point and line and then say, oh, by the way, they're not defined. We don't know what these words mean, but we're going to use them anyways. And we're just going to, our theories are going to be founded on them. So the guy says, look, we have a point here. Well, what are you talking about? Are you talking about that little dot you just put on the board? No, it's a location. That's just a pictorial representation of a location. So they're telling you, look, we represent love with a heart. So every time you see a heart, you're supposed to think of love. That's what the guy's telling you. Or like I say, you want to represent goodness. You put an angel. So you say, well, that's an angel. No, no, but see, don't look, you're being too literal. The angel represents goodness. You know, you're going to heaven or something. So this is the problem. The problem is they put a dot and they say it represents a location. They put a line and they say it represents an itinerary, a bunch of locations. And that's where we have the problem, or a length or a distance. That's where the problem is. They're inconsistent. First, they're inconsistent. Second, these are not geometric figures. And all I'm saying is, if they're going to use, if they're going to say that what they're intending is to have a series of locations, a series of, series of locations, or a length, or a distance, or a bunch of numbers, you know, a number line, then they should not use the word line. They should tell us exactly what they mean. Be literal. Why use euphemisms? Why use figures of speech? Why talk in parables and in tongues? Say it like it is. Bunch of locations, movement, displacement, length, whatever you think it means. Don't tell me line or point and mean something else. Okay, with that, I'll see you next time, and hopefully you do some research on line and point and go crazy like I have. We'll see you then. Bye-bye.